Right, yeah, so I start there. Yeah, so the origin of intermolecular force. Well, we say molecules, they attract, okay, especially polar molecules. Okay, so you might want to add a description here. So polar molecules attract due to the presence of like a charged ends. Okay, so polar molecules attract each other. What about non-polar molecules? Yeah, even non-polar molecules attract each other. But why is that? You see, non-polar molecules, they do not have like a particular part of the molecule with more electrons, right? So for non-polar molecule, well, just look at this molecule. Does it have one atom in the molecule with more electrons than the other? No, right? Both of the atoms have just about the same amount of electrons, right? You see? But you see, electrons, they don't sit still. Okay, they will move around. Okay? So inside a non-polar molecule, yeah, so even non-polar molecules attract each other. This is because, okay, so I'll show you like a few diagrams here. Okay, so starting with this one. At the beginning, I have two chlorine molecules sitting next to one another. They don't have any particular atom with more electrons than the other. But then suddenly, one of the chlorine molecules, okay, they will have a distortion in the electron cloud like this. And then the next instant, so what you're seeing here is this is what happened at t equals 0 second. This is what is happening at t equals 0.0001 second. And this is what happens at t equals 0.0002 second. You don't have to remember those time stamps, but you should know that at the beginning, the two chlorine molecules, they don't have particular positive charge and negative charge at the very beginning. But because electrons, they don't sit still, they like moving around. Occasionally, you'll find one molecule with one of the Cl having more electrons than each. It just happens. It's just because electrons, they don't stand at this position. They will sometimes move more closer to the right-hand side Cl than they do to the left one. So causing a delta positive and delta negative end to suddenly form on even a non-polar molecule. So can you put down some short notes in here? Because electron moves randomly, okay, just like in an atom, you see in an atom, electrons, they will move around the nucleus, right? Randomly, right? Yeah, so in the molecule, the electrons will also move randomly. Yeah, in a molecule, therefore, okay, this ClCl molecule will suddenly acquire a positive and negative charge. Okay, so a delta positive and a delta negative charge. And you see the other guy. The other guy at the beginning, it doesn't have any delta positive and negative yet, right? But because it's under the influence of this molecule here, with more electrons being around the Cl, can you tell me what will this electron do to the electron on this end of the Cl? Do electrons attract or do electrons repel? Each electrons, they are all negatively charged. So negative charge, they repel. They repel, right? So therefore, the electrons that accumulate on this Cl, they will repel the electrons that are on this Cl. So pushing the electrons over to the other side. So this is why when you get a delta plus and delta minus on one molecule, you will also get that on the neighboring molecule. Because the electrons here, they are not immune from these electrons. These electrons, they will exert a repulsive force on these electrons, pushing them over. This is why you see a boundary on the neighboring molecule. And it is because of this that we say there will be delta positive and negative charges on both molecules, and eventually they attract. Okay, so these two attractive forces, we coin a name to describe it. We coin when the Waals force. Okay, so can you put down what we call these attractions? These attractions are known as when the Waals force. Right, so are known as when the Waals, make sure you spell his name correctly. So when the Waals, the apostrophe come after the S. Okay, so when the Waals force. Okay? Right. Now that we know when the Waals force exists in polar and non-polar molecule, we need to know what can influence the strength of when the Waals force. There are two factors. One is the size of molecule. The other is the shape of molecule. Okay, but any question you want to ask me on this page? No. Okay, so we saw two things on this page. Number one is that there are two types of intermolecular force. The second thing we will also learn on this page is that when we melt or boil simple molecular substances, only the intermolecular forces has to be broken. The third thing we learn on this page is the origin of when the Waals force. How does when the Waals force arise? Okay, so how does it form? Okay, and once we know how it forms, we can turn to the next page and look at factors that, this is more important, so factors that affect the strength of when the Waals force. Okay, so strength of when the Waals force. There are just two factors. One is the size of molecule. So you can put that factor 1, size of molecule. You want to write this really large. So size of molecule. And that, put that in relationship here. We say when the Waals force strength is directly proportional to the size of the molecule. Meaning, have you seen this symbol before in math? Yeah, proportional to. It means when the thing on the left goes up, this thing will also go up. Okay, so this is what proportional means. So it's proportional to the size of molecule. Yeah, so write down this relationship for me. And then we have factor 2 on the side, okay, which is the shape of molecule. So the shape of molecule. So this is factor 2, only 2 factors. We say when the Waals force strength is this time inversely proportional to the degree of branching. So how do we interpret this relationship here? So when you see this sort of relationship, we say when the Waals force and degree of branching, are they directly or inversely proportional? Inverse. Do you know what inversely proportional means? It means when we make this number larger, you know what happens when you divide one by a larger number? It will become smaller, right? So this means when this goes up, this will go down, or vice versa. When this goes down, this will go up. This is inverse relationship. So write down this on the side. When the Waals force strength and degree of branching, they are inversely proportional. And you can draw an arrow here to explain what that means. When this goes up, this goes down. That's inverse. Okay? And on top, when we draw like a connection between these two factors, we say they are directly proportional this time. Because when one thing goes up, the other also goes up. And when one thing goes down, the other also goes down. Directly proportional. So when this goes up, this also goes up. This is clear. Okay? So now we look at some examples. Okay? Let's start with, let me put this on the side. Okay? So we have some examples here, starting with the halogen. Okay? So compare Cl2, Br2, and I2. So which of these do you think has the highest melting or boiling point? Do you remember what are these? These are halogens. Yeah, and in what order do they appear on this periodic table? Is it chlorine that is smaller, or is it iodine that is smaller? Chlorine, yeah, chlorine is smaller. So that means we can draw these chlorine molecules here. Yeah, they interact through covalent bond, but we are not looking at the covalent bond here. We are looking at the intermolecular force. You can see that these forces of attraction we call when the Waals force is not very strong. because Cl2 is not very large a molecule. But when you look at Br, just look at Br. Br is like a slightly fatter version of Cl. Okay? They also connect by covalent bond. But again, it's not the covalent bond that we're interested in. We're interested in the intermolecular force strength. You see, it grows stronger because the molecule grows larger. And what happens when iodine, when we look at iodine? Well, iodine is like a supersized version, okay, of a halogen you see here. So they also connect by covalent bond, but the covalent bond is not what's to blame for their high melting point. Instead, it is the van der Waals force strength. So you can see in here. Can you put down this inequality sign? In terms of melting or boiling point, chlorine is lower than that of bromine, and bromine is lower than that of iodine. So can you write down the logic here? Okay, the explanation. Number one, from chlorine to iodine, the size of molecule increases. And what happens when you increase the size of molecule? What happens to the van der Waals force strength? It grows stronger. So point number 3. Van der Waals force strength increases. So does it take more energy or less energy to separate the molecules for iodine? More energy, yes. So therefore point number 4 is that a lot of students miss point number 4 and so they lose a point in the exam. They have to say more heat is needed to overcome the van der Waals force in I2 than in Cl2, which explains why the melting or the boiling point trend goes in this order. And it also explains the state. Do you know what states does chlorine exist in?
Yeah.
Guess. What about bromine?
Liquid.
Finally, iodine.
Solid.
What about the color? Because just now when I came from the Form 6 class, even they don't know what the color is for chlorine. That's bad. I want to make sure you know. Yellow is green. Yeah, yeah, it will be right. So can you put down the state? So this is a yellowish green gas. This is a liquid, a red liquid, okay, and this is a black solid. Okay, so write down the color as well. So I don't want you to not know the color. So this is yellowish green, and then we have orange liquid, almost like blood, and then you have a black solid. Okay, right. Now we turn to something else. What about the shape of molecule? Okay, so let's compare. So you all have learned isomers, right? Do you remember? Well, maybe not isomers. You all have learned how to draw organic compounds, right? So do you know how to draw a 5-carbon alkane? Well, tomorrow we have a test.
Oh, yeah.
What is the formula of a 5-carbon alkane?
C5H10.
No. Alkane has general formula CnH2n plus 2. So what is 2 times 5 plus 2? 12. So to correct your answer, C5H12. Okay, alkane is CnH2n. Alkane is CnH2n plus 2. What does an alkane have that an alkane does not?
2 more.
The CC double bond.
Oh.
Right? Yeah, that's what it is. Do we all agree that an alkane has double bond that an alkane does not? Yes. Well, then let me just make sure that the 3 of you know what it will be on the test tomorrow. What is the name of reaction that alkane undergo? Is it addition or is it substitution? Substitution. And for alkane to react with halogen by substitution, what needs to be present? Sunlight.
Somewhere failing.
Oh, this is bad. Okay. Do you remember that when alkane reacts, they will need UV light, right?
Yes.
But when alkene reacts, they don't need UV light. Okay. Well, let me just make sure you know this. Okay, by putting it here. So a very quick summary on alkene and alkene. This would definitely.
So it's gonna be a test tomorrow, right? The things.
It's going to be on the test. Well, so you know the other students, they will be missing out, but fortunately, well, no, we have to let them know, okay?
No.
So for alkane, the first thing that I might ask you, okay, is the general formula. So what's the general formula?
CS2
For which one?
for alkene.
Alkene will be CnH2n. Alkane will be
CnH2 and 2
plus 2, CH2 plus 2. And N must start from, what is the simplest alkane you can think of? What? CH4. Because alkane, they don't have CC double bond. That means they don't have this restriction that says they must have 2 carbon. They can have just 1 carbon, that's fine. But alkenes, they have to have either 2 because of the second question. What is the functional group? So functional group is a reactive part of the molecule. What is the functional group of alkene?
Double bond.
CC double bond. And for alkane, actually,
None.
none.
No.
Yes.
Silent.
At least for this part, you remember. Okay, good job. And so can you draw some examples of alkane? So this is the first alkane. What do you call this alkane? What do you call these 3 alkanes?
CH4.
Well, that's not how you call it. That's the formula of it. So methane, ethane, and the third one is propane. Yes, propane. Remember, math minions eat pure banana. Okay, METB. Okay, this will definitely be our test. Okay, we don't want this to come to the test. That's bad. Okay, we don't know this. Now, let's try something harder. What about this one? So these are the simplest alkene I can think of. Oh, and just now, when I come back from the Form 6 class, I still see them make this mistake. What is the problem?
5 bonds.
Yes. Make sure none of you make this mistake. I don't want to see 5 bonds on the exam paper, please. Okay, so we have this. Wow. Can you name these alkenes for me? Yeah, there will be a question on
Protein
the
is for propene.
Yeah, the top one will be
Ethene.
ethene. So write down ethene, ENE. Okay, not ANE anymore. What about the second one? Propene.
What about 2E?
Yeah, what about this one?
Butene.
If this is butene, what about this one?
No.
The number. Number. Where do you put the number?
2. That's butene. That's 2 butene.
Do you want E?
And it is 2E, right?
Yes.
Yeah.
Oh, okay. Yeah, remember this number?
Skeletal formula is easier than this.
Oh, really? You sure? You sure about that? Okay. So, well, let's see. What do you call this alkene? Be careful what you wish for. Okay.
Has 2E.
What are these things?
2 methyl. No. 2 methyl X 2E.
What about this one?
No, 2. 1, 2, 3. 2, 3 methyl X 2E.
So,
Die.
Yeah, this is what might appear tomorrow. I mean, this type of this level of difficulty. Okay, and it's pretty like standard type of question you have to remember. So has 2E. 2 means the double bond starts at carbon number 2. Dimethyl. Okay, yeah, you must know that a methyl group means carbon, 1 carbon group. And why di? Di means they are 2 of the same group. So 2, 3 tells you that they are attached to the main chain at position 2 and 3. Well, this you must know, okay, for tomorrow's test. Okay? Yeah, I hope that the other student can watch this video later. But anyway, yeah, the next thing that we will look at is the reaction. Okay, so the reaction with halogen Okay, so halogen means H2. And H2 can be Cl2 or Br2. So when we react alkane with halogen, so can you tell me what will happen? When I react this with chlorine, can you predict the product and the name of the reaction? So what is the name of this reaction? Is it addition or is it substitution? Substitution. Alkane undergoes substitution. And substitution has this requirement for UV light. Okay, so UV light is needed. If there's no UV light, substitution cannot occur. Okay, so can you draw an arrow here and write down UV light? No UV light means the reaction cannot progress at all. Yeah, and what does substitution mean? Remember, substitution means something goes in, something comes out, right? You can look at chlorine as ClCl and think about what the word substitution means. Substitution means something goes in, something comes out. Can you predict the product when I swap one H for one Cl? Or I think you mean CHCl, CH3Cl. Yeah. But you know, after substitution is like a completed ones, there are still some H's left, right? So that means these H's, they can continue substitution further to form, what is the next product you can think of?
ClCl.
C,
CH2Cl2.
yeah, CH2Cl. What is the third one?
CH3.
Yes, if you are confused, try to draw them all out, then you will see that one at a time, you can swap an H with a Cl, and so their formula are respectively CH3Cl, CH2Cl2, CHCl3, and CCl4, and I want you to name them all. What do you call the top left one?
Chloro.
Yes, perfect. Excellent. Okay, so chloromethane now. Okay, there are three of you here. So the other two of you name it. Yeah. Maybe Eric first. The second one here. So if this one is called chloromethane, do you remember what did we say when we see two of the same group? Yes. Dichloromethane. How many carbon do you see?
2.
Carbon. One. It is one carbon throughout, right? So dichloromethane. So now you have D. The third one. On the left. If two okay, right. But you know, tomorrow's test is individual work. Okay, like I was saying, if you together all your answers, all of you will get full marks. But sadly, tomorrow's test is individual work. Okay, so make sure you revise. So trichloro and tetrachloromethane. Right. And there's a product that I forgot to add. Do you know what that is? Think about it. When something comes out, something has to go in. And right now we are only looking at what happens to this part when the Cl goes in. What about what happens when the H comes out? When the H comes out, when it joins with Cl, it forms. You know, when this goes in, you get this product. And when the H comes out, when this H comes out, HCl, yeah, you do biology, especially into
You missed something.
okay, right, yeah. So, yeah, we have also, okay, so we have HCl. Right, so this is HCl. So what do you call this product? Hydrogen chloride. Yeah, I know in biology you call this hydrochloric acid, but we don't call this hydrochloric acid here because there's no water. Okay, so can you cross out? You can write out the wrong name here for hydrochloric acid and cross it out and explain why. So not this because no water.
So is then hydrogen chloride gas?
A gas. Yes, it's a gas. Okay, so hydrogen chloride gas I should add. Okay? Yeah, so that's substitution. So yeah, Alex, remember, tomorrow there will be questions set on
That's the
alkane
answer.
and
Actually.
alkene. So make sure at least the four of you know. If the four of
Sir,
you also do
we're
not know
not
the
friends.
answer, I will quickly
We're
say
not
today.
friends.
Yeah, so for alkene, if alkene undergoes substitution, what is the name of the reaction that alkene undergoes? Addition. Yeah, and addition don't have such complicated requirement. It doesn't need UV light. Whether or not you provide UV light, they will react. Okay, so addition. No, or you can just say does not require UV light. Meaning, with or without UV light, it will just happen. It will just happen. And can you help me predict the products here? So we have, this is the substitution reaction. And then in here, I want you to try this addition reaction here. When you react C double bond with 4 H's on the side with bromine, can you tell me what sets substitution apart from addition? Substitution means something goes in, something comes out, right? That's what substitution means, okay? Addition means two things react to form one single thing. So therefore the arrow, be careful. They only go in, nothing comes out. This is what addition means, okay? Can you predict the product? So sketch on your notebook. Draw out the product. Name it. Name it.
Dibromo.
30 seconds.
Dibromo. No.
Dibromethylene.
No.
Something to in because those.
No. Oh,
No,
when
it's
you,
single bond.
it becomes a single bond. Yeah, when it
Oh,
goes
the
in.
bracket, the
Oh.
bracket. Yes.
No, not the bracket.
And then the things.
Can you see that these 4 H's they remain unchanged, right?
It's
These 4 H's they were there, they are still here after the reaction. It is only the Br takes out in.
dibromoethane.
Still, you are missing a number.
1,2-dibromoethane.
Yes. Then never forget the number. Okay, so if you miss the number, I will mark it as an incorrect answer still. Okay, so
0.5, sir.
1, 2. Well, no, the name only worth 1 point. So if you miss 1, 2, you will get
Sir,
0.
0.5.
No, we don't have 0.5 since A level. Yeah, back in the days in A level, yes, you get 0.5. But trust me, you will find it really, really hard to get those 0.5 marks there. Because for a 6 marker, there will be 12 points if I chop the marks off into 0.5, 0.5, 0.5. Yeah, so trust me, you don't want to see a 0.5 system in your exam. So this is dibromo ethane, yes. And just like Lee has pointed out, the double bond is gone after addition.
Right.
So don't draw double bond in here. And to make things worse, don't make it like this. Okay, because this will have 5 bonds as you connect to each carbon. That's not a real structure. So what color change will we expect here? What is the color of bromine we just mentioned?
Orange.
Orange or red.
Dark orange.
Yeah, dark orange or dark red. It will turn into a
Colorless.
colorless substance. Okay, so remember this color change. We call this test bromine test. Okay, bromine test for unsaturation. So we have orange turning into colorless. Yeah. So therefore, what do we say? We have the test for unsaturation. Unsaturation means C double bond. Only things with C double bond can react with bromine and produce a color change from orange to colorless. Okay, in the absence of sunlight. Yeah, so because you see, if you provide UV light or sunlight, even the alkane can react, right? So when you test, let's say I'm giving you 2 test tubes, one with an alkane, one with an alkene. If you want to tell them apart, I'm giving you a sample of bromine on the side, okay, for you to add to both of them. Will you want to add the bromine into the alkane and alkene in the dark, or do you want to do it in broad daylight?
Dark.
In the dark. Because if you do it in broad daylight, I can tell you both test tubes will react. The alkane one will react by substitution. The alkene one will react by addition. So if they both react, you don't know which is which still. So therefore you switch off the light. You pull down the window light. Okay? And now you redo the experiment. Only alkene will react this time. Because the alkane, due to this limitation, that they require UV light. When you switch off the lights, when you put down the window blind, no UV light comes in, substitution cannot happen. So it will stay
Light bulbs.
orange if you use bromine. Yeah, but chlorine is yellow is green. Okay, yeah, so just now I like to miss something. Okay, we talk about, you can refer back to the video later. But basically, when the Waals force depends on two factors: size of molecule, the bigger the better, or I should say the bigger the stronger. Okay, yeah, so yes,
Not about super solid. It's about
the size of the molecule.
Size.
So for example, when you look at chlorine, you know chlorine is a gas, but iodine is a solid, right?
Yes.
Yeah, why is that? That's because the molecular size of chlorine is smaller. So this is what each Cl2 molecule look like. It's this small. And this is what each iodine molecule looks like. It's much bigger. Yeah. So therefore, we can put down this conclusion in here. The bigger the molecule, the stronger the when the Waals force, and the higher the boiling point. Okay, so the stronger the when the Waals force, and the higher the boiling point. Now we look at another factor here. Okay, on the side, which is the shape of molecules. So now I want you to compare the boiling and melting point of these molecules. So starting with C, 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 C. Look at these 5 carbons. What do you call this compound? Pentane, yes, okay. And here's another compound with the same number of C and H, just that they are arranged differently. Yeah, if you count, you will still find 5 carbon and how many hydrogen? What is the general formula of alkane again? C and H2S plus 2. When you plug 5 into N, what do you get?
C5.
Okay. Yeah, if you set C5H10, that's pentene. That's not pentane. Okay. So make sure you bring your calculator tomorrow. Okay. So and then we have this guy. So this is also a relative, okay, a distant relative, okay, of these the first 2 molecules. It also has 5 carbon, 12 hydrogen. So what do we call molecules with the same number of carbon and hydrogen atoms? We call them isomers, okay? So you all remember isotope.
Yeah.
What are isotopes?
Atoms on the same
Neutron
element, but without the
difference.
same neutrons.
Same proton number,
Different
different neutron number. So now learn a new word today, okay? So we have isotope, we have isomer, okay? So isomer is new, isotope shouldn't be new. If it's new, you should start revising from form 4.
ISO
Okay.
means the
So-
same.
Yeah, iso means same, okay?
What
So,
language is this?
yes,
What language is ISO?
English. In biology, there's isotopic.
It's like Greek or like Latin.
Maybe it has Greek or Latin origin, but this is so common a word in English language that.
Let's learn Greek.
Okay, yeah, isotope. They are atoms of the same element with, okay, so with number 1, same number of protons, different number of neutrons. Don't say same proton. Of course, the protons are all the same. Yeah, the proton from carbon is the same as the proton and nitrogen. It's the number that is different. Okay? Think of protons, electrons, and neutrons as building blocks. Yeah, if we are 2 different chefs, we can make a complete different dish from the same ingredient, right? Using a different number of them. Okay, even if we start with the same ingredient. Same number of protons and different number of neutrons.
It's the physical difference.
Yeah, so what about their qualities? Okay, if they have same number of protons and therefore same number of electrons, do they have same or different chemical property? Same, yes, because which particle here, proton, electron, or neutron, controls chemical property? electrons. Okay, so write down because of them having electrons, same number of electrons. We don't say similar. They are exact same. Okay, they have exact same chemical property. It's not even similar. It's more than similar. Okay, so same chemical properties. And what about physical property? Which particle or particles? Neutron and proton combined. Okay, because proton and neutron together they form the mass of the atom. So this will determine their physical property. Physical property. See, form 30. Okay, yeah. So different physical properties, e.g. mass. Okay, e.g. reactivity. Okay, so you know, just walk down from the house and just go in for just 1 second. You go there. Okay? Yeah, and if you don't, it's just a matter of time. So okay, isomer. Okay, isomer. So isomers, they are molecules. Okay, with put this down, same molecular formula. So you might remember like this. Molecular formula means the total number of atoms. So this is the total number of atoms.
With different arrangements?
Yes. Okay, we call that this structural formula. So can you write down? But different structural formula. Correct. So structural formula is the connection of atoms. So the number may be the same, but the connection, the arrangement of atoms is different. Okay. So different attachment of atoms. Okay. So yeah, different attachment. So here we have some examples. Below we have chlorine 35 and chlorine 37. So let me give you all a very short task. Can you tell me how many protons, electrons, and neutrons are there in these two isotopes?
17 protons.
Yes. How many electrons? The number of protons and electrons are equal in atom.
18 neutron.
Neutron. What about electron? 17. Okay, for proton and electron. So the number of neutrons in the first example is 20, and the second one 18. Yes, because 37 minus 17 is 20, and 35 minus 17 is 18. Okay, now we look at isomer. So isomer is new to you. So we have isomers like C, 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 C. So you can see 5 carbon, 12 hydrogen. We have C, 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 C. Yeah, so you have 5 carbon and again 12 hydrogen. And finally we have C, 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 C. Okay, so can you tell me which of these has the most branches? Leftmost or rightmost? Rightmost. Okay, so and which of these do you think has the highest boiling point and melting point before I tell you the answer?
Right.
The rest of it is top or the bottom? Highest melting point.
Bottom.
So you think it's bottom. Actually it's the
Highest.
top. Yeah, why? So let's take a step back from these molecules. Okay, take a step back from this molecule. What do you see? For the first molecule, let me shrink it so you can
It's
see
like
more.
a fractional distillation.
Yeah, like in fractional distillation, you see it is, yeah, it's related a bit, okay. But can you see, if the molecules are straight chain, like in this example here, can they come close together or can they not come close together? They can come real close, right? And if they can come really, really close, that means they can interact, okay, more strongly, okay? What about the middle one? Let me shrink it again. Can you see that thing sticking out? The branch that is sticking out is preventing the molecules from getting too close. It's like it's holding out a hand and saying, "This is my safe distance. Don't get anywhere near." Okay, any more closer, and then it will just point this at everybody around it. So it prevents the molecule from getting too close. So you see, it is already much weaker because of that branch sticking out. And you see, with this molecule, it is even more dramatic. You see, so it has 4 hands sticking up now and say, get away, okay? So the molecules can come near as close as in this molecule and as this molecule. So therefore we can see that the strength of intermolecular force go in this order. So this is the strength of intermolecular force. So the thickness of those dashed lines represents the strength of the intermolecular force, the van der Waals force. So what is the conclusion we can draw here? So from this to that, we say, number one, as the degree of branching increases, as there are more branches, so you see the first guy has no branch at all. The second guy has one branch. The third guy here has two branches. Okay, so you can, okay, let's just call these the branches. So two branches. So as the degree of branching increases, the surface area of contact between the molecules decreases. Okay, so this is the surface area of contact. They can touch all over their surface, right? Yeah. But what about the middle molecule? The middle molecule can only touch at this surface. So this is the surface area of contact. The third molecule can only touch at these points, even smaller. Okay. So the surface area of contact between molecules decreases. Okay, so the surface area of contact between molecules decreases. So this results in the van der Waals force strength decreasing. Okay? Yeah, so this is the second factor that affects the the strength of intermolecular force. So let me dumb it down into a few sentences on here. So this is the concluding sentence that you must know. Okay, so I'll put this in here and write. The more branches there are, so the more branches there are, the smaller the surface area of contact between molecules. Okay, surface area of contact between molecules. And the third point here is the weaker the van der Waals. Let me just copy this part. So the weaker the van der Waals force and the lower the boiling point. Okay, so the weaker the van der Waals force and the lower. So because you see the more branches you have, the lower the boiling point. This is why we say there's an inversely proportional relationship. Because when one goes up, the other goes down. Right? That's what inverse means. Inverse means when one thing goes up, the other goes down, and vice versa. Okay? And what about on the left? What we see on the left is a type of directly proportional relationship. Because the bigger the molecule, the higher the boiling point. So that's direct. Okay, so no direct and inverse. Okay, they are different here. So any question on this part first? No? Okay, so we will now look at the hardest type of intermolecular force yet. It's hydrogen bond. Okay, so we are halfway done with this chapter. So now, over here, you can finish copying this first.
Chapter 26, right?
Microscopic world, I don't remember the chapter number, I only remember the head. It's microscopic world 2. Okay, yeah, because in this big topic there are many subtopics. Okay, yeah, this is one of them. The other ones are polarity of bond, polarity of molecule we discussed last lesson. You have to still remember them. Okay? Right, next up we have hydrogen bond. Okay, so let's take a look at hydrogen bonding. Okay, so hydrogen bond is a very strong type of intermolecular force. Okay, so this is a very strong type of intermolecular force that is not van der Waals force. Okay, so intermolecular force found exclusively in polar molecules. Think of this as like the VIPs. Only the elites, only the VIPs can have hydrogen bond, can enjoy hydrogen bond. Okay, it's not like something commoners can have. Okay, so exclusively found in the elites. Okay, so these elites are polar molecules fitting the following requirements. With HN, remember just now in the lesson I said north, HN, HO, and HF. Okay, so yeah, I like to think of it this way. So can you compare this with the when the Waals force we just saw? When the Waals force is shared by all molecules, okay, yeah, common on not everybody has it, okay, when the Waals force. So let's do a very quick comparison. This is weaker type of intermolecular force that is found, not exclusive anymore, so found in all molecules, polar and non-polar. Okay, so polar and non-polar. It doesn't say any requirements on who gets to have when the Waals force. Everybody has it. Okay, so therefore to check that you really understand what I'm saying, so let me highlight this. In polar molecules with HNHO, HF bonds. On the right, polar and non-polar molecules can have that. And the other difference is that hydrogen bond is extremely strong when the Waals force are weaker. Okay, and the one on the left is exclusively found in certain molecules. Okay, so for example, when you take a look at this, let me give you 3 molecules. Okay, so question: identify the type or types of intermolecular force present. So you can put an umbrella term on top of hydrogen bond and van der Waals force. They are both under intermolecular force. But these 2 forces, okay, sometimes only one is present, sometimes both are present, okay, depending on the molecule. Not that they are both under intermolecular force. They are like the first type and the second type. You may or may not have both of them. But let me tell you, one thing is for sure. All molecules, regardless of their nature, they must have van der Waals force. Okay? So this is like it's like asking, oh, what's the similarity between all of you? Well, being human, okay, it's the similarity of all. So this is the minimum. Everybody will fit this requirement. But you know, some people, they will have some additional features that others do not have. Okay?
So they have both bonds at the same time?
Yeah, they can have both at the same time, yes. Okay? So and below we are going to look at those examples. Let's take a look at CH4. First of all, is it polar or is it non-polar? Remember, anything with just C and H in them, they must be non-polar.
Non-polar.
Okay, so let's write down non-polar molecule. Yeah, and then we put down a key, a very important note on the side. Okay, you should write it down as well. All hydrocarbons, meaning compounds made of C and H only, okay, must be non-polar. So all, no exceptions. So all hydrocarbons, e.g. C6H6, CH4, or anything, okay, must be non-polar. Because what are the only type of bonds present in hydrocarbons?
Van der Waals.
The bond. What kind of bond do you see in?
Non-polar.
Is this CH or it's CH and CC, right? Yes. When you think, oh, I don't see any CC bond here. Well, that's because this is the simplest alkane. What is this next simplest alkane? C2H. When you put 2 into N, what do you get for alkane? This is alkane. This is alkene. When you put 2 in, what will this become? 6. So C2H6. Okay. So the next alkane here would be CC, like this, C2H6, right? So this is why I say hydrocarbons, they will either have CH bond or CC bond. And both of these bonds, they are non-polar. Remember that table from before, from way back? Where was that table? Yeah, I'm trying to find it just right there. I think it's way. Oh, here. What do we need to ask ourselves if we want to know if a molecule is polar? We need to first check if they are polar bonds, right? Like I just said, hydrocarbons, they can only have non-polar bonds, right? So therefore, what do we answer for the first question? Does the molecule have any polar bond for hydrocarbon?
No.
No. Always non-polar. You don't even have to think. Hydrocarbon always non-polar because you will always answer no for any type of hydrocarbon. I don't care what the formula is for the hydrocarbon. They can only have CC and CH. That means you will Answer no, straight away. So they are non-polar. So this will not appear in the test yet, but that doesn't mean that you don't have to know it, okay? Like right now, because this is way past the test, right? This concept. So can you put down all hydrocarbons must be non-polar. That means they can only enjoy which type of these intermolecular force? Van der Waals. So think of this as like something that everybody has. Okay, yeah. So this you don't even have to look at whether it's polar or not because everybody has it. And these are the VIP. Only the VIP can have it. Okay. And to check if the molecule is VIP or not, we check the structure. So let me show you one more here. This is H2O. Is H2O a polar or non-polar molecule?
Polar.
Polar. How do we know it's polar? Because when we compute the electronegativity difference between the atoms, it is larger than 0.4. What is 3.5 minus 2.1?
0.4.
1.4.
1.4.
Yeah, 1.4 is way larger than 0.4, right? So what does it make? Does it make for a polar or non-polar bond?
Polar.
Polar. So what will we answer for the first question?
Yes.
Yes. And after we answer yes for the first question, we have another question. Do the dipole moment cancel? Do these dipole moment in water cancel?
No.
No. Okay. This is when they will cancel. This is when they will cancel. But this is not when they will cancel. Okay. If they do not cancel, the molecule is polar. Okay. And H2O fits an additional requirement. Is that do you see NH, OH, or HF bond?
OH.
You see OH. So that means it is the the VVVVIP. Okay, so it has a polar molecule with so you have in here polar molecule with OH. And I want to add one more here. Okay, so let me just add one more in here. I have HCl. So is HCl polar or non-polar? Is HCl polar or non-polar?
Polar.
Polar. Why? Because the difference is
0.9.
0.9. 0.9 is larger than 0.4, right? So it is polar. Okay. So but then what should we put in here? We will say H2O is polar molecule with
Hydrogen bond.
with OH bond. Okay, and then I don't know why just now I moved it away, but then now it's back. Okay, so we have HCl. So here we say it's just an ordinary polar molecule. Now let's check some boxes. Okay, so this will be the last part of today. We have the type of intermolecular force. So type or types of intermolecular force present in each. So let's check these boxes here. We have number one, van der Waals force. Remember van der Waals force is enjoyed by all kinds of molecules, okay, whether they are polar or not. So we have van der Waals force. And then we have the one we serve for VIP, okay, hydrogen bond. So when do you expect to see van der Waals force and hydrogen bond? So for the first one, it's present in all of them, right? Van der Waals force. Van der Waals is present like everywhere because as long as it is a molecule, it will have it. Okay, but it is stronger for polar than it is for non-polar substance. So you see, these are non-polar, right? Yeah. So therefore, they have van der Waals force, but these are weaker. These ones they are polar, right? So they are stronger. Okay. So I wanted to put down a box around here and write down non-polar molecules have weaker van der Waals force. So non-polar molecules have weaker van der Waals force than the polar molecules. So polar molecules have stronger van der Waals force. So what about hydrogen bond? You will only expect to find hydrogen bond in which of these molecules?
H2O.
H2O. So cross, cross, take, cross. Okay? Yeah, and then now we can use this to, like, put these molecules in order. Okay, so can you just compare molecule A, B, and C? So you have A. Let's leave out D for now. Okay, they won't set such a hard question and ask you to compare also D. Let's just compare A, B, C, and A and B and C. So let me make it a question on the side. Question: compare and explain the difference in boiling point in A, B, and C. Okay, so difference in boiling point of A, B, and C. So let me copy this over again here first. Oh, I missed the H there. Okay, doesn't matter. So let me add this back. So you have A, you have B, and you have C. So first of all, which of these molecules has van der Waals force A?
Oh.
All three, right? So you see van der Waals force all have them. So this has, and this has a stronger type. Okay. But what about A and B? Comparing A to B, which of these can have a stronger van der Waals force? Remember the two factors that determine van der Waals force strength? Size and branching, okay? But you can see none of them have branches, but one of them is larger. Which one is larger?
B.
Yeah, so B is larger. So therefore, I'm going to put two texts here, okay? And you will see why. So this is the reference, okay? It's nothing special. The ones on the right, they are compared to it. So compare B to A. Why would B have stronger van der Waals force? Larger size. So can you put that in a short commentary here? This is the description. Okay, so B is stronger than A. Okay, in terms of the in terms of the van der Waals force. Yeah, that's because the molecule C2H6 molecule, the second molecule in the middle B, C2H6 molecule, is larger than CH4, and because van der Waals force is related to size, therefore the van der Waals force of B is stronger, right? Yeah, than A. Yeah, what about C compared to A? Now why would C have an even stronger van der Waals force than A then? Because of it being polar, right? So remember, polar molecules have stronger intermolecular force than non-polar molecules. So van der Waals force, C is greater than A. Yeah, so maybe you can also put down for B, this is larger non-polar versus smaller non-polar. So a larger molecule compared to a smaller non-polar molecule, it will of course have stronger van der Waals force. What about C and A? C is a polar molecule and A is a non-polar molecule. Remember which one has stronger van der Waals force? Polar. Yeah, so therefore you can say now, because H2O is polar, but CH4 is non-polar. Polar substances have stronger van der Waals force. So this is why, while I put take for all these three molecules, you see this is, well, you can say it's almost twice as strong. I wouldn't say exactly it's twice, double as strong or twice as strong, but this is stronger than it. And this is even stronger than these two. Okay? So CH4 is non-polar, and polar substances have stronger VDW than non-polar ones. Is that clear? Okay, we have just one more thing to consider before we wrap this up. Okay, so then non-polar ones. So the second type of intermolecular force we need to consider is H bond, hydrogen bond. So which of these has H bond?
H2O.
H2O. So this has, but the others do not. So now you can add them up. Van der Waals force plus H bond equals over IMF strength, over intermolecular force strength. Can you see that when you add these two up? And when you add these two up, you can see a trend here. Yeah, that H2O has stronger, intermolecular force overall. So this is why the boiling point should be in the order of C Okay? Yeah, so is that clear? So so this is A, this is B, this is C. Therefore, we say the boiling point also follows the order. Because boiling point relates to the intermolecular force strength. The more strongly the molecules attract one another, the harder it is to boil. Okay, so this is why they are directly correlated, these two. Okay, so we have A smaller than B, smaller than C. Is that clear? Yeah, that's basically what you need to know in this chapter. Okay. Yeah, of course I will work on some questions in the next lesson. And on Friday I've arranged with the lab technician I will confirm with Canada that we will do a qualitative analysis. Basically, I'll give you sample test to use. I will not tell you which is which, but I'm telling you here are the 5 substances that you'll find in test 2 ABCD. If not, but they are out of order. Yeah, I mean I scrambled the order. And you have to mix them together to deduce which test contains which chemical. This will be this Friday's task, okay, the triple lesson. Okay, so yeah, but I'll let the other students know tomorrow before or after the test. Remember, there's a test. This is the end time I'm letting you this, okay, so there's a point, okay. So,
Upload the things.
yes, I'll upload this and the video. No, okay, we'll be this selfish, okay? Yeah, we have to, I'll upload it by tonight. And whether the other students read or not is up to them. They haven't come to this class, so I can only do my
Why are they still
best.
here?
Okay?
I thought they should be on me.
Why did you guys have to take part?
What?
Because he doesn't want to do that.
Wanna go.
Then you skip it.
That's tired.
Okay, I'll see you tomorrow, okay?
Yes.
Finish the test on time. I think the test will last for 45 minutes or 40 minutes. 40 or 45. Because last time I heard some feedback from the students that they haven't got enough time to finish. When a lot of students on the back, they are just sleeping.
True.
I
So
don't know
the
what
students in the back don't bother doing it.
I don't know why they even provide
Only
all.
for D class, those
I really don't get yeah. So it's not this words in form 6, okay? So, but yeah, I mean all of you are doing your part, you're doing well. But I just don't get why some students I mean it's just form 5, it's not even form 6. I mean in form 6 when you get overwhelmed by a lot of stuff, I understand. But not in form 5, right? I don't know what they're doing.
They don't care about it. They don't